Alright guys, after recording the whole lecture one time and figuring that my microphone was off, I'll re-record it again. So here we go, this time should be better then. So last time we talked about the first derivative test and how that would help us find the intervals where the function was increasing and decreasing. And to do that, we use the first derivative. Now, if we take the derivative of the first derivative, that is the second derivative, then we can determine the concavity of a function. So a function that looks more or less like this would be a concave up function. It means it opens up. And a function like this would be a concave down. Okay? So what happens here? Well, let's look at the first derivative at for this function at this half of the function. So here the function is decreasing, so it's going down. So the derivative then is negative because the function is decreasing. When the function becomes increasing, the derivative of that function, let's call it f, is positive. So the function is going from the derivative, of the function is going from negative to positive. So the derivative itself is increasing because it's going from a negative to a positive, say in the y coordinate. So for the derivative is going from negative to positive, so it's going to be increasing. So on this whole interval, the second derivative, which is the derivative of the derivative, is positive because the first derivative is increasing. Now in this case, the first derivative is going from positive to negative. So that tells you that the first derivative itself is decreasing, and so since the first derivative is decreasing, the second derivative is negative. So we say a function is concave up when its derivative is increasing, or equivalently, if the function is differentiable, the derivative is differentiable, the second derivative is positive. Now, we say the function is concave down if, under the right circumstances, the second derivative is negative. So if we want to determine the concavity of a function, or look at the intervals where the function is concave up and concave down, then we would have to look at the points where the second derivative is 0 or not defined, and at those points we will possibly have a change of sign for the second derivative. So in that case we would have points that are called of inflection. So a point where the concavity of a function changes is called a point of inflection. So let's go ahead and calculate those intervals where the function is concave up and concave down for the particular function that we have at hand, that is f of x equals x to the fifth minus 5x plus 2. So what do we do? Well, just what we did for the first derivative test, except now we don't need the first derivative, we need the second derivative. So calculate the first derivative just to get your second derivative. So you calculate the first, and to calculate your second derivative, that would be the derivative of the derivative. So you use this expression now, and the derivative of the derivative would be 4 times 5, 20, x to the 4 minus 1, 3. So, and the derivative of a constant is 0, so that is our second derivative. So when is this function, this second derivative, undefined? Nowhere. Where is the second derivative equal to 0? Well, the second derivative is equal to 0 whenever 20x cubed equals 0, which you can solve it and you get x is equal to 0. So this is our only possible point of inflection. Okay, so we use those possible points of inflection to divide our real line into intervals. So for example, we go from negative infinity to 0, and then from 0 to positive infinity. So do we care, for example, about the point where the first derivative is 0? No, because we're determining concavity. So we care about possible points of inflection. When we did the first derivative test, we cared about those relative extrema or those critical points. Now we care about those points of possible points of inflection. By the way, I should be a little more careful. The possible point of inflection would be the point on the graph. So the x-coordinate is 0, and the y-coordinate, you would plug it into f, would be 2. So the possible point of inflection is the point 0, 2 on the graph of f of x. In any case, we choose test values in our intervals. So -1 and 1 leave in there, and we evaluate our second derivative. When you plug -1 into f double prime, you get -1 cubed, which is -1 times 20. That's negative sign. We just care about the sign, because that in this case is telling us the function is concave down, just as I mentioned a little earlier. Now when you plug x equals to 1, you get 20 for the second derivative, positive 20. So that is positive, and it tells you the function is concave up in that interval. So that's how you analyze the concavity of a function. Now I mentioned that we don't really care about the critical points, and that is just partially true. We will care about them whenever we look at the second derivative test, rather, and we'll do that in the next video. So just to close this, let's take a look at the graph real quick, the graph of this function, and you see how the function is concave down between negative infinity and 0, and then from 0 on it becomes concave up. That matches concave down. I should draw some arrows there, and concave up. Okay, and you can see that's exactly what we got in our table. Alright, so that's that for this video. In the next video we're going to do a quick example of how to use the second derivative test. Thank you for watching, guys.